welcome. This is the second panel of this this event. I am Valerio Schiavoni from the University of Neuchâtel, and I'm very glad to see also Christelle Pieszurski. Perfect. Who is also another of the members of the board of directors of the AHUG. So welcome everyone. The format of the panel is the one that I'm going to describe next. We'll be giving each of you a couple of minutes to introduce yourself. And then we will go through some questions. We have a bunch of questions already there for us, let's say, to kick off the discussions, and we'll be also taking questions from the audience in case there are others. So maybe I will go through the list of names that I have. Maybe Andrew Younge, can you introduce yourself a little bit, please?
Sure, I'll go first. Hi, everybody. I'm Andrew Younge. Can you guys hear me all right?
Yeah, we can.
Yeah? All right, cool. I'm a computer scientist at Sandia National Labs, and I work on the Vanguard program, among other things. And Vanguard is an advanced technology prototype effort that we have to investigate emerging technologies in HPC and their applicability to the DOE and NSA mission. The first application of this is Astra, which was the first petascale ARM supercomputer and has obviously since been superseded by Fugaku. The initial focus of this machine was on enabling the ARM ecosystem and investigating its applicability to our HPC needs. We've also done a lot of work in this space on advancing the state of HPC system software as well. Thanks.
Thank you, Andrew. The next in line would be Ross Miller from the Oak Ridge National Lab.
Okay, hello everyone. My name is Ross. Oh, you're able to hear me?
Yes, we do.
Okay. My name is Ross Miller. I work at Oak Ridge National Lab. I'm a software developer. It sounds like I have a very similar job to what Andrew just described. Primarily, I'm a software developer, but I've also been for the last few years managing our much smaller cluster that is not anywhere near as big as Astra, but is our sort of technology demonstration and evaluation cluster for ARM. And we have at this point, it's a heterogeneous cluster where we've got ThunderX2s, we've got GPUs, we've got the Fujitsu processors now. So it's an interesting test bed for just trying out a variety of different ideas around ARM.
Very well, thank you. Do we have Gilad Shainer from Nvidia in the audience?
No, I don't see. Or we should wait a little bit. So go through someone else.
Let's wait.
Yeah.
Carson Woods from the University of Tennessee, on behalf of the Spac project. Are you
can you guys
connected?
Hear me?
We can.
Yes,
we can.
Awesome. So my name is Carson Woods. I'm a student researcher at the University of Tennessee at Chattanooga. In the past, I've done collaboration with Sandia, working on transitioning the advanced TriLab software environment which was the software environment initially on Astra, to one that was built with, from one that was built using RPMs to one that was built using Spac, which is a open source HPC package manager. As a part of that, I've worked on just, getting all sorts of software running on ARM and just contributing to the Spac project and improving the software ecosystem on Spac. And so I've been contributing features and patches to improve that compatibility and interoperability for use on Astra and ARM in general.
Thank you. Thank you. That's a nice summary. Terje from the University of Oslo. I saw you connected before.
Yeah, thank you.
There you are.
Yeah, my name is Terje Kvernes, and I am the head systems administrator at the Department of Mathematics at the University of Oslo in Norway. As part of my volunteer work for EASY, the European Environment for Scientific Software Installations, I began the process of ensuring that our EASY build-based software stack could be installed and run on ARM64, much as similar work as Carson and trying to see what worked and what didn't work and what we could push upstream to, well, generally speaking, provide better scientific software support for our ARM clients.
Thank you. We also have John Linford from ARM.
Hello, John Linford. I'm, sorry, can you hear me? There we go.
We do.
I'm ARM's director for HPC application performance engineering. So I run the team of HPC experts that sit around the globe and try to work on site with our ARM partners and end users on their HPC applications. We also run a heterogeneous cluster of ARM server class systems in Austin. So we have some experience installing and maintaining systems in that way, as well as working with the applications out in the field. So our responsibility really is to try to interact with the end users and in a sense be ARM's first customer when it comes to the HPC space. We're not trying to sell anything. We're really just trying to understand how these technologies are being used and how they can be improved.
Very well, thank you, John. And at last but not least, Dan Ernst, HPE.
Thanks. Yeah, I'm Dan Ernst. I'm a distinguished technologist at HPE. I work in an advanced technology and architecture team. I do a lot of the node architecture actually, and I came over from the Cray acquisition last year. But in particular, I've spent a lot of the last half dozen years working on ARM technologies, everything from working on the development of SVE and trying to understand how compilers can really well apply to it, and vice versa, as well as working with a lot of our performance engineers and tools engineers on internal systems and figuring out how to, where do certain technologies apply, how well do these different ARM technologies perform, working on, optimization and all that good stuff to help figure out what the best way to bring ARM technologies to our customers is.
Thank you, John. This is Dan, sorry. So I think we, all our panelists introduced themselves. Is that right? We were maybe still waiting for Gilad if he joined. Not yet.
No, looks like no.
No, right. Okay.
No,
Then
sorry, he's here. He's just
he's here. He was.
Oh.
Yeah, so I've promoted him. He should be along soon.
Oh, okay.
Okay,
Then,
yes. But he has no micro on, so it would be difficult to hear. Oh.
So unless there is a microphone appearing, otherwise maybe while this is being set up, we might want to kick off the discussion. I would like to ask the audience if you had to list the top two most challenging areas of deployment for the ARM-based systems at your location had to face. What would those two be? Is anyone happy with this question?
Sorry, could you advance the slide, please? I'm still seeing on-site experiences.
It was not. Yeah.
Thank you.
So, anyone wants to comment on that?
I'll go, sure. Hi, I'm Andrew Davis. I'm from the Kingdom Atomic Energy Authority. I think the biggest issue we faced was probably the software ecosystem. Not that ARM doesn't already support a vast range of scientific tools. It was that the particular set of one of the things I wanted to try after doing my main tasks, the tool had a particular dependency which wasn't currently supported. What exactly that was right now, I can't quite remember, but it was not something available on ARM, and it was going to be quite painful to make it work. That was the only thing I can think of.
So I can mention one that's not on here, and that is firmware immaturity. When we first deployed Astra, we ran into this time and time again. I don't think this is unique to ARM, but rather a unique new processor. from a company that hadn't deployed something like this at this scale as a server class chip. With any system like that, being it ARM or otherwise, I think you are and should expect some firmware immaturity and some bugs early on. That's part of how it goes, I guess. But that was certainly a challenging area for us, and I would expect that for any new system being rolled out, along the similar lines.
We experienced some of that too. For a little while, the ARM Forge team was testing DDT on our internal cluster, and then we thought that DDT would kill A64FX nodes because every time you open the debugger, the node would go down. And then eventually we realized that it just only affects certain users. And then we realized those certain users happened to be using BGFS, which was served over InfiniBand. So in fact, it had nothing to do with DDT or even the user. It was the firmware that we had on the IB card in our node. And once we fixed that, it looks like it's going to be better. But exactly, it's a bit of a surprise.
Yep, and again, a lot of those things should be expected for any first of a kind supercomputer deployment. So.
Okay, anyone else wants to comment on this?
Well, the problem with software dependencies is something we saw quite a lot of when we started porting parts of the easy stack to ARM. Things that were written specifically with x86, 64 in particular in mind, and having to essentially start filtering out dependencies and adapting essentially dependency stacks for ARM. Not a lot of it was actually problematic as much as it just needed work, and a lot of it is simply, unfortunately, that people expect a certain platform and code towards that. They often don't necessarily know much better, and that problem with basically familiarity and outreach is something we see a lot from the scientific software we were poking at.
Okay,
that's something that we frequently run into an issue a lot with Spac packages, is that many packages are built for different architectures, x86, Power 9. The focus is just not immediately on ARM, and as such, a lot of people are just not as familiar as the different kind of nuanced things that you have to do to, get around certain software stack immaturities. So that is something and that adoption is being improved. A lot of packages are being updated to include support, and out of the box, if software supports it, it should, sort of air quotes, just work. But many times that's not the case, and that's something that's improving. But it's definitely a challenge that some packages out of the box they didn't work quite as easily as just having Spac install the package as you might expect on other systems.
I think part of my concern with that, honestly, is that I totally get the argument from some people we contacted with patches. And I said, this will make it work on ARM. And the response was, well, sure. But as has been pointed out to me as well, how do I test it? When they don't have access to test systems, they're reluctant to take the patches and actually do anything more than just say, okay. And that's, I hope that'll get better. And I think it'll get better. But right now, that is actually our concern. Whether or not people use something like a Graviton from AWS and CIs or something like that, sure, but not everybody is there, especially not scientific programmers.
Yeah, I will second that. It's less about the software ecosystem. I think we've shown that has a lot of merits and is something that we can use in production. It's more about sort of having an integrated development environment. That's the hard part, and we're making strategic investments in that. We've been leveraging unprivileged, on-premise container builds for that. Building and investing in CI is another good area. So I think that's a great suggestion.
And I was just going to add one thing to what Carson had said, and we do use Spac packages on the cluster I manage. And yeah, the vast majority works and everything. The problem comes along with everything's going along great, especially with something like Spac, where you just do Spac install one package and it starts pulling in all the dependencies, and you get all but one of the dependencies. but you need that last one. So it's one of those things where, you know, we're 99 or 95 or 99% there, but yeah, we still got that one last package we've got to get, whatever that one is. To the credit of the Spac team, every time I've submitted a patch, they've been able to take it, and we're rapidly running out of things that don't work. So I'm very pleased in that regard. I think when we did our latest upgrade, I did not have any problems with Spac packages that wouldn't build. But yeah, it's one of those things where you have to get all the way there. You can't just be 99%.
Well,
Right,
it's-
exactly.
I think
really
part of
kind of
the
a-
concern, though, for us with when looking at the easy build environment and the easy stack in total, is that yes, we can maintain these patches and we can keep doing that, but neither Spac nor the easy build developers can sit on these patches. It has to happen upstream sooner or later, because keeping track of what's going on upstream while you're trying to make architecture patches work downstream is not viable long term. So as Andrew said, having a good CI offering for people who are developing scientific software is going to be, I mean, it's also going to help the community, not just with regards to ARM, but in general for scientific software, to have a bit of, let's call it developer, basically doing development better, because a lot of scientific software has some minor issues here and there that could be better.
That's a nice way of putting it.
I try to be polite. I've been working with TensorFlow a fair bit, so.
So it seems in the end, if we want to summarize this discussion, the top two most challenging areas would be software ecosystem and integration with existing systems. I would suggest to try to see what's next for our panel and see if this can trigger another nice discussion. Unless anyone has some pending comments on this, I would move on.
Just one quick thought. I wonder how much of these issues are ARM specific, or they're simply a reflection of a new processor, right? How many of these things come up when a new x86 comes out, when a new PowerPC comes out? Is this ARM, or is this just ecosystem in general?
No, this is ecosystem in general mostly. And Andrew kind of pointed at this, but anytime you get a new architecture, right? I mean, we're doing all this tools and development, right? For all the gray tools, for example. And, you know, we optimize version of our compiler for each new thing that comes out. And when it's moving from, you know, Intel Haswell to Intel Broadwell, that step is pretty small, but it's still a step, right? You know, moving to a whole new company doing this stuff, like, you know, Marvell took on, I guess, Cavium at the time, or whatever instance you want to talk about with ThunderX2, was new to this whole field, right? And getting a real server firmware and all that stuff was not something they had done. And even with that, I think we were pretty successful in getting, as a community, you know, to a point where it was functional and relatively useful. At least as a way of cleaning out a lot of these correctness problems, right? There's always one more package that still has x86 intrinsics in it, but I think the hope is, now that we've done pretty much, you know, most of this architecture porting for functionality, the rest of it from here on up becomes just performance tuning for each new platform, right? So then it's, as an example, TX2 to A64FX, you're moving from you know, ARM v8 Neon to now, okay, now we have to add SVE. Well, all those Neon codes are going to work on that chip, right? It's just a matter of now, let's add the performance tuning, you know, going forward with your advancement. So hopefully the steps get shorter, and less painful, less correctness, more performance, maybe the way to put it.
So yeah, I agree. And I'll take a second to make a shameless plug for our paper at SC'20, the Chronicles of Astra paper, where, I mean, we really outline what we've done with Astra, but they're not unique to ARM, right? There was a couple of specifics that were, but in general, it's about what do you need to stand up a, you know, first of a kind supercomputer. Of course, I'll point, you know, try to encourage people to take a look at that paper, but I think we've made a lot of progress, and we can leverage that progress quickly with ARM. Whereas any other architecture, other than x86, I guess, you got to start from the ground up, and that is a significant investment.
I just very briefly like to point out that I totally agree with Dan that we've gotten far. My concern is still with not necessarily the software we're fixing today, but the software that gets written tomorrow. Because that might, unless people know better, you'll see things like, is this a 64-bit CPU? Sure, I'll check if x86 64 is defined. And yeah, those lessons need to be learned and taught.
Thank you for these final remarks. Let's move to the next question. So let me read that out loud for everyone. So if ARM-related vendors had to focus on only one area for HPC systems, which area would you suggest? Who's going to take this first? It's a tough question.
So I guess I'll speak up and comment on my own point here. I think we're at sort of a walk stage in a crawl, walk, run sort of, 3-set phase with ARM. I'd really like to see that run stage being embracing heterogeneity and building a pretty expansive, ecosystem that's beyond just ARM, but about the, assembling of multiple different vendors and specialization, potentially within a single architecture, encompassing architecture. I really see this as a huge opportunity for ARM, and I really hope we can, in the next couple of years, see that kind of come to fruition.
So some answers include compiler tool chain.
Yeah, I was gonna, I'll just toss in my own experience thus far with having just put in the Fujitsu processors last month. It looks to me like the processor architecture is racing ahead of the compiler developers' ability to keep up. We've seen just in the difference between GCC 10.2, which is the latest released version, and a build of GCC based on their Git repo, that there was an enormous improvement in the speed of, which benchmark were they running? They were running the Stream Triad, and just changing compilers changed that. And Stream is, that's not even a CPU benchmark; it's a memory benchmark. So I think we still need. I think the compilers that we've got, at least, I haven't had a chance to try the Cray compiler yet. But I think the compilers we've got access to at ORNL are still catching up to the architecture. And of course, the architecture is racing ahead as fast as it can. So
yeah, I agree,
some more effort on the compiler side, I think.
A64FX is by virtue of how it was developed, it is the first of a kind, right? It won't be the last, certainly, for SVE, but it is the first, the first mover. And so, yeah, the software has to keep up with that. And upstream, there is SVE support in things like GCC. Because it was a strategic thing for us, we dove right in with it. And so, yeah, the Cray compiler, I'll take this time to pitch that Heidi Poxon, who's the head of our programming environment group and the tools team, is giving a talk at the hackathon tomorrow about the tools that we're developing there, both for obviously compilers and toolchain pieces there, but libraries for scientific computing and all that stuff, right? These are all things that we developed over time, but are being deployed on this new Apollo 80 product, which is how we're shipping the A64FX to folks. It is super important, and we've spent a lot of time internally doing our own tuning and learning how these architectures, right? And again, to the prior point, SVE is a new instruction set, but the performance aspects of it and the ability to compile for it depend heavily not just on the instruction set, but the implementation. And the implementation for A64FX is unique compared to what you might expect if you came from working on AVX 512 or something, right? So there's a lot of work there to go. Again, my hope is we keep that to being performance improvements over time, and it will catch up. The upstream stuff will catch up. There is some challenges, as Andrew brought up, about the heterogeneity of the ARM ecosystem, meaning you're going to get a lot of different things that all say SVE on them, and they're all going to perform very differently. And so the tuning of those is going to be an interesting question over time.
I think people are often surprised to find out that it's easier to update hardware than it is to update software in most cases, right? Like the GCC that comes with your Linux distro is going to be massively out of date for most of the time that you have it installed. And it's just true that the hardware tends to race ahead of the software, and we're used to buying our system and then updating the software over time. So the idea that it's actually easier to fix it in the hardware usually is a bit strange, but it is really the way it works.
Well, that's with GCC actually being ahead of the game on SVE, right? LLVM is not there yet as well.
That's a good point. Absolutely. Yeah.
Well, with that, it's important to point out that support versus optimization are two different things, right? And
exactly
one
that.
is far easier than the other.
Yeah, totally. And in that sense, it's also like one of the suggestions here, or topics is to offer consumer ARM hardware just to get with the same instruction set and the same capabilities, simply to get it out there, to have people be able to work on it in a little bit more of a distributed fashion. One of the things we ran into was simply that we wanted to try building stuff, and just getting a hold of the hardware to, test things meant that people had to go through, well, usually specific individuals to get access to specific hardware to be able to test things. And that takes time, and it requires a lot more effort. And let's face it, everybody has access to x86 with the specs you want. That's not hard. So I hope we get there, and I hope it'll be fun to see what happens when Apple starts shipping ARM hardware in their laptops. We'll definitely have an effect on it.
Actually, I think it's really interesting that nobody said interconnects anywhere, right? There's nothing. I wonder, does the community actually think that we're there with InfiniBand and Tofu and all the rest? Like, is that sufficient? Because it feels like there's not really that many options. If I'm saying it, I'm just curious if anybody else feels that we could be doing better there, or is it enough?
I can only speak for myself when I say that we haven't gotten to that problem yet. Like, there are other things that we're missing to the point where we're going to go, well, you can't build TensorFlow, or you can't build this. So, how your interconnect works is, if it's good enough and works, then okay. It's optimal, maybe not, but at least we have something that works.
No, but this is definitely a good point. It's you can look on the interconnect from two angles. One of them is just the ability to connect ARM-based servers together, and then make sure that the drivers are there, or any sorts of accelerations are there, and all the network tools and the fabric management and things of that sort can run on an ARM-based system. The other angle, which might be more interesting, is that the network start to include its own computing engines. Meaning you have devices from our side, for example, the Bluefield devices that are actually DPU, data processing unit, which means the network adapter, it's a combination of a NIC and multiple cores of ARM on it. And now you have actually a data processing unit that sits directly on the network, and it can be used for isolations and security, meaning you can move the infrastructure management out of the server and run it on the DPU device. You can actually move security. You can do encryptions and decryptions on the network. You can do completely isolations between users on that. And you can take even further. You can virtualize storage access, meaning that the DPU can become the place where the application mounts storage, and actually everything from that perspective, the DPU handles with the cluster file system or the network file system and so forth. And the last part is that you can also migrate MPI libraries or AI deep learning libraries like Nickel and others, and actually migrate the non-blocking elements of MPI and run them on a DPU. So the network is much bigger aspects. And by the way, most of the questions and answers are kind of looking on the simple way that I have an x86 cluster and I have an ARM cluster. What does it mean? But the supercomputing platforms are basically something that is starting to evolve or continues to evolve. And now you get ARM cores on the network everywhere. It's a different element, and I don't think that no one actually look on that as part of the answers. And I bet that's probably going to be the same for the rest of the questions. But this is something that we need to think about it. And I think that you will see new supercomputing architectures being built and trying to move supercomputing. And sorry that I'm having a long answer.
No, it's fine.
I think from a supercomputing perspective, by the way, the number one today that you look on supercomputing is performance, right? How do I get bare metal performance? How do I squeeze anything I can get from that? How do I deal with users and isolate between users and protect between users? That's a secondary thing, right? This is one of the problems that you need to deal with. Now, with DPUs, you can actually create a new architecture of supercomputing. You can create an architecture of supercomputer which is more cloud native in a sense, meaning you can move the infrastructure management. That's what I mentioned before, and run it on a DPU, not on the host. So you can get bare metal performance on one side. You can have like completely isolations and security on the other side, and actually a room for actually doing accelerations. That's something that we think will become the new generations or the future generations of supercomputing architectures. And that's exactly by leveraging ARM cores that are not as the host CPU, but actually in a DPU sits on the network.
Very interesting remarks. I'm not an expert in the field. I was wondering what would be the relation with energy efficiency in general. No one has mentioned this so far, and how is there any interest?
Well,
There's always interest in energy efficiency as these things scale up to many megawatts. I think this is a possibility for advancement in the ARM ecosystem, but I also would push back in saying that ARM is a naturally, the ISA is somehow much more naturally energy efficient. There's a history of that work, and that can be leveraged for server class platforms, but same time, these server class chips still require a certain amount of energy, and that should be expected independent of ISA.
Yeah, from the software side of that too, what we've found over time is that there's two takes, right? One is obviously there's power management and doing a good job with that. And that actually comes back to the firmware conversations we were having earlier, right? We need to make sure that we have good power management firmware, which by the way, that software also runs on little ARM cores. The other piece is that at the application level, what we found historically is that the most energy efficient way to accomplish your workload for HPC is to get it done faster. Right. So performance and energy efficiency are actually pretty much 100% interrelated. Right. There's outliers and exceptions you have to be careful about, but this is generally what we've seen looking at this. Right. From a software angle, what we'd hope is if we get better performance libraries, better optimized things, it will just sort of naturally also be more efficient, right? Besides any hardware changes and hardware difference.
Okay, thank you for these answers, multiple answers. Let's move to the next question. Yes, let's go here. So let me read this for you. How can existing software stack for ARM-based HPC systems can improve? It seems there's a cluster around maturity and stability. Almost. full consensus there.
I'd like to make a comment with regards to the both questions that have come up for attendees, both from the Q&A and the chat with regards to ISO language standardization and portability, which is also part of the stability and maturity situation right now. And we actually found code that was perfectly valid and ran perfectly fine on one platform, but didn't on others because GCC simply isn't identical for every platform. So you had language constructs that simply didn't work on one platform, which was it was a bit of a surprise, but there was no surprise on what platform it did work on. And that was just unfortunate, to say the least. And we had a number of those situations that, they blindside you. I really didn't expect that, to be honest.
I think there's a very good question here in the Q&A box pointing out that, how do we do CI/CD and perf testing today? Mainstream hardware availability still seems very problematic. Testing on ARM as getting an ARM chip is quite easy in through different cloud providers. But the harder problem is convincing people to do it in the first place. I think it's pretty true that to be honest, I'm actually kind of surprised to see so many dots under maturity and stability, because many of these software stacks, while they do have corner cases, the corner cases are usually due to people making false assumptions or bad coding practices, things that would have been fixed by good software carpentry practice, a good CI/CD implementation. It's more of a human problem than a technology problem, I would almost say. It really does come down to just writing the code well in many cases. Okay, response. I don't want cloud. I want direct developer access to affordable workstation server class hardware. Now that's a very fair point, right? And Linus was very famous on this point. But I think read the news. There's some interesting developments coming out from ARM partners. I'm legally not allowed to say more. But I think you're absolutely right. I have an ARM laptop, which you can't see because my camera is doing this thing. But I also have an x86 laptop because I can't exist in a pure ARM world yet in a client device. It's just not quite there. But I hope it will be soon.
There's actually an interesting comment from Kenneth where saying that the lack of good practices is also there for x86, and if you need to have everyone using good practice before getting wide adoption, then you're in trouble. Which kind of makes sense to me.
Yeah, I mean that's true. Like x86 got widely adopted, and then it wasn't for there was still plenty of people doing bad things with the software. So bad software
people are
practices
still doing bad
obviously don't prevent hardware from being adopted.
Sorry.
And just if there's a little pause in the question, I'm kind of curious. I know whoever was asking about CI had said they wanted direct access to hardware, which is fair enough. I'm kind of curious though, if for all of these, like the Amazon Graviton instances or whatever, has somebody just put together a container with the CI software ready to go, so that it's easy to just deploy your container on your remote instance and save an awful lot of hassle of setting all of that up every time?
Well, I'm actually working on something like that for the Easy project right now, using Terraform and similar structure to automatically generate both the build environments and test environments and tearing them down when you're done. And yeah, it works really well, but I mean, it goes back to what Kenneth said in the comments, that if you're starting to demand that from your software developers who are scientists sitting there working on a PhD or maybe doing a postdoc and writing some code, it ain't ever happening. We need to be able to provide that in an environment where they can just say, please test this code and make it, see if it works. Because we have enough problems trying to get people to, oh yeah, Python 3.8 came or 3.9 came out. No, sorry, things don't work, and the test, they haven't getting it for a different platform. No. So again, it goes back to what I'm going to mispronounce the name, but Cesar said in the Q&A that if you have access to the hardware yourself, if it's on your desktop or on your laptop, then you will actually test for it.
So yeah, to
I
build on
disagree
that, as
with
you can
that
see behind
statement.
me, there's a whole lot of hardware that we have on premise and available. And one of the ways we're trying to make this more accessible to developers is through unprivileged containerized builds. We've done some initial prototyping with Podman and have some success with that. It's still a little rough around the edges. There's similar work being done with Charlie Cloud as well from Lanel. I think these are all interesting opportunities, and we're going to see this be a very different space 6 months to a year from now, not only due to increased hardware availability, but increased build infrastructure that then gets enabled and it enables a new set of CI efforts.
A similar effort is being undergone by the Spac project. They're trying to use the AWS Graviton to do CI/CD on package pull requests. So when changes and improvements are made to Spac packages, they will just be automatically tested on a variety of compilers and architectures. And ARM is eventually going to be one of those. But it's not implemented yet. But that's something that is actively being worked towards as well.
And that's the same state that we're in. But again, from the chat, I mean, we have what do we do with the long tail of scientists, who are writing code on the side, and this isn't their primary job. Getting them to use a container, looking at something like integration towards, like more of an integrated framework towards commonly used source repositories, like be it GitHub either on-prem or GitHub.com. Whether it's Bitbucket locally or GitLab, whatever you're using, for us as administrators and framework like what Andrew's doing, and trying to prevent or to offer to people, this is how you set up a testing environment. Just add these little bits of code to your repo, and we will take care of the testing backend of it. That's basically where we need to get, I think, not just for ARM, but in the like pointed out, that what happens with performance when you get the next chipset. Does it actually work? You see performance go down in some situations because GCC isn't quite ready yet. So to be able to use something like a reframe or something similar to keep testing and make sure that things actually work, it's not easy.
So we are moving to the next question, and since we still have 15 minutes before the next panel starts, and I still would like to cover all the questions that we have. This one is still regarding so what features would you find most useful in a future ARM cluster or supercomputer? Here, there is not such a clear consensus as before, and people are casting votes for chip level capabilities, accelerators, power efficiency, memory systems. Most of the votes go for there. Do you agree?
I would point that this slide is actually one of the reasons that the ARM ecosystem exists, is that everybody has different things they need. And if you're able to diversify through an ecosystem instead of relying on one or two vendors, you have the potential to get a variety and not just one or two things, right, that serve one or two workloads. And we're entering a period now where architecturally it's really hard to make gains in a general purpose sense that outpace what you could do if you actually tune your architecture one way or the other, right? From a design point perspective, if you look at A64FX, it hits some of these bullets and it hits other ones less so, dependent on the workload that Recon has, for example, right? And so, this makes perfect sense to me that the desires are broad, is because people have different needs for their workloads. And again, one of the purposes of the ARM ecosystem is that you're able to start serving more than one of these at a time.
Well, I think it's probably telling too. If you remove the word ARM from that question and replaced it with any other CPU architecture, I think you'd have about the same distribution of things that people want. That's nothing to do with ARM. That's just who wants a faster supercomputer.
Absolutely. And it's very application dependent. What one application I have wants is completely different, or sometimes very different than what a different application may want. Being able to leverage all of that in a single ecosystem, I think, is a bit of a holy grail moment for HPC. But yeah, that I agree with Dan's comments especially. This is what is exciting, and this really spells out the potential that I think ARM has in this space.
I would say not much features. Like if I was going to vote on here, I don't actually want any one of these. I assume that every one of these is available in any one of the systems I have available to me. What I want is a system that maximizes that aspect of the performance of the system I'm running on. So when I run my application on a system that maximizes memory bandwidth, I want my application to adapt to that. Or it has a high powerful, interconnect. Let's take advantage of that. ARM is a great common denominator between different architecture designs, but unless you tune, you only get the common denominator performance. So that's what I would really be excited to see, is some way that it facilitates performance portability between these different features of the future supercomputers.
I admittedly have not seen a cup holder offering yet, so count me subscribed there.
I could certainly use one to hold my cup. Right?
Okay. Great. Okay, this is just regarding the presentations. I think we can don't need to discuss on this unless anyone has a special comment regarding that, or so.
One thing I would point, by the way, if you go back, if you can go back to the previous one, I'd say that the Nvidia UCX on ARM, it's not actually the Nvidia UCX, because UCX, it's a framework that is coming from the UCF consortium. It's completely open source. I'd say that Nvidia is a member of UCF, a proud member even, I would add, of UCF. But UCF include also other entities such as Los Alamos National Lab and Argonne, and there's contribution from Oak Ridge, and ARM and AMD and IBM and Huawei, and I'm probably gonna miss few others, and sorry for that. Ohio State University, another entity. So there is a lot of work. It's actually a community effort. And UCX, it's a framework or library for point-to-point communications, and very high performance point-to-point communications that is portable across multiple platforms, including ARM. So it's greatly run on ARM. I would also add that UCF as a consortium has some other projects that are completely related. There is a project that is called UCC, which is create a framework for collective operations. UCX is point-to-point, UCC is collectives. There is another project that is called OpenSNAPy, which stands for Open Smart Network API, which actually defines an API or start API to enable the services of DPUs or enable the services of ARM cores on the network to be simply accessible for folks writing applications. So there's multiple projects as part of UCF. I think that presentation, by the way, covers some of those. And I do encourage people that are interested to look into new generation of frameworks, point-to-point collectives, APIs, and things of that sort that enables great performance on supercomputers as well as ARM-based supercomputers. Take a look on the presentation, or even probably even better to check out the UCF consortium website, and you can go through all the projects and hopefully find some interested and join the effort.
Okay, thank you for this pointer to this project. There seems to be a set of open questions. Let's go in order. What is the best compiler toolchain for ARM64? What's the difference between ARM64 and AR64? Anyone wants to answer this?
It's gonna have to either be Dan or me.
You know what my answer is? I think it's pretty obvious. We have had a production ARM toolchain, production level optimized ARM toolchain since probably 2017, I think, something like that. And have had we have been compiling SVE code since before it was called SVE. So we have a lot of work behind us. Obviously, it's a sort of a limited space tool chain because it's really focused at HPC specifically on our systems. But we're hopeful that we're able to provide the performance that shows what these chips can do. Sort of at full capability, and the open source ecosystem is going to catch up eventually.
So it's a bit of a loaded question. If you look at University of Bristol, they do a great side-by-side comparison, compiler comparison for different applications. I have to say, as somebody who runs a field team and encounters real-world applications in anger, the GCC compilers are pretty decent, especially starting with the more recent GCCs, the GCC 10 and 11. The open source compilers are catching up. But at the end of the day, it depends on your application. It depends on what Fortran features you need, what level of performance you need in certain math intrinsics. It varies widely. Practically the only difference between ARC64 and ARM64 is one of them has more vowels than the other. They're just two ways to refer to the same thing.
I would say one thing, John, when it comes to picking your compiler, or for that matter. My experience has been very simple. Whatever compiler you like to use, make sure you're using the latest one.
That is especially true for newer architectures.
Yeah.
As I think Ross mentioned, right, the difference between even recent GCC versions is really large. So, and this is the case of the software trying to catch up with the hardware, right? It'll make big improvements in the short term, for sure.
Yeah, I'd just like to make the argument that to answer that question, it really depends on what architecture you have at hand. Because our answer for, say, the ThunderX2 chips versus the A64FX chips, which my colleague Cy Hammond's going to talk about, I think, next, and has a talk in as part of that next panel, are completely different. So it really depends. And I think it is a moving target, as many are alluding to here.
Yeah, and to be clear, for all of our systems, we always want to make sure that there are at least 2 compilers available for everybody, because as Andrew points out, right, everybody's code is going to hit a different point on a different compiler. And what Simon and his group at Bristol have shown pretty much lines up with that.
I have a question though for, particularly Dan in that regard, which you just said with offering multiple compilers. How do you inform the user base on what they're supposed to be using? I mean, that's something I run into regularly when I talk to my users. And how do I direct them to the stack that actually is best for them? Because a lot of them aren't computer scientists. They see that code runs and are happy with it. We even had a minor issue at some point in, we're not going to say exactly where we found out that people have been running TensorFlow on CPUs only because the code was compiled with the wrong compute capabilities, so it never actually hit the GPU. Nobody reacted for 2 months. I mean, how do you have any guidelines for users like that?
I'll give a first order bit because, for us, it's really about enabling, right? Not about the management of multiple. So we do have obviously our own module support in our software stack that allows people to basically swap out one programming environment kind of wholesale for another. So you can basically enable one module, compile with, GCC and all the appropriate libraries, and then you could switch modules to the Cray PE and then go compile with that, right, with all the appropriate modules and libraries. The management of that is getting more complicated, or in some ways more complicated, but also in some ways easier as we're trying to do things like integrate with Spac support, right? To make the whole flow be something that you can kind of program in at one point and then just let it go. Right? I don't know if Carson has more to say about that kind of stuff.
I mean, from a Spac perspective, Spac offers the ability to load packages. It generates module files as you would expect, but it also has the ability to load specific packages through Spac. And so you can load based off of, I mean, without going into too much detail, you can install obviously concurrent versions of the same software with different optimizations and different variants and built on different dependencies and different versions of dependencies. And as part of Spac, you can simply ask Spac to load a specific version. And so that might help. It might sort of point users to the kind of desired package by showing them what is different in a more kind of readable way, rather than just putting out a list of module files that is kind of up to system administrators to name and organize in a way that is coherent. But that is still a challenge that we face as well. I mean, if you just let Spac do its thing and then you rely on module files only, you're going to get a lot of module files with a package name, package version, and a really long hash at the end, and it doesn't look that pretty. So that's a challenge that that we would face as well.
So I can try to answer that question with maybe not the right answer, but at least what we've done. And that was with the Advanced Tri-Lab Software Environment, or ATSE. We really tried to provide an exemplar programming environment and software stack that users could directly leverage. If they wanted to bring in their own software from that, if they wanted to change their Spac profile, all that's still possible. If they want to bring in their own container, great. And I think it's important to have both that sort of leadership programming environment that you provide targeted towards one or more ecosystems or hardware types, while still enabling that larger flexibility. It's a careful and delicate balance, but it's an important one to get right.
Well, we try when we're looking at something like the Easy project to offer, I mean, single software stacks across multiple platforms, multiple architectures, and multiple microarchitectures. So sure, users can then pick what they want. They can try to compile their stuff. They can run it. They can do tests, and they can see, you know, this runs great on ARM. This runs great on another platform. This runs great on this microarchitecture within ARM. And this is great. I mean, I love the fact that we're offering that to our users. My problem is that a number of my users aren't there. They, you know, whatever runs my code now, that I'll use. And it's up to you people to make it run fast. And I'd like to try to help them, but, you know, it doesn't scale very well when everybody starts to use HPC.
We are crossing our time slot, and especially the next panel is already gathering people and soon to be started. Maybe I would like first to thank all our speakers: Terje, Ross, Andrew, Dan, Carl, John, Andrew, and Gilad, and Carson. So please feel free to join the next panel. I'm very glad that there was a very lively discussion, and I hope people enjoyed. Well, remember, this panel is being recorded, so you can watch again if you want to, and feel free to get in touch.